Okay. So hello everyone, and thank you so much, Juan, for the kind invitation. So today I'm going to talk to you a bit about some of the research topics that I'm currently working on. And one of them is automation in the Open RAN ecosystem. And specifically, I'm going to show to you some research on how to automate the deployment and the testing over the air and also on emulated environments of a cellular network in an end-to-end manner. So basically, in a manner that you test the component that you want to test as part of the whole ecosystem and not just in a confined environment. But first, let's make a step back and see a bit about the recent evolution of cellular networks. So we have that in the last few years, cellular networks have undergone a significant change from what was monolithic architecture. So for example, by monolithic architecture, we mean that we have a traditional single unit that takes care of the functionalities of a base station, which is the one that you see here on the bottom left part of my diagram on this slide. And this unit was in charge of doing pretty much all the functionalities of the base station. So from the lower layers, so RF and physical tasks, to higher layers like MAC, RLC, PDCP, and it was all taken care by a single unit. So while this worked for prior cellular generations, with next generation networks, we have that these functionalities are not anymore taken care of a single unit, but they're split among different units. So they're, as we say, disaggregated into different components. So for example, you can see in the diagram here that the layers that I had here, I don't know if you can see my pointer over here. Maybe let me switch to laser pointer. Nope. So the layers that I have over here on the left are found now in different components, like for example, the CU component, where we have both user plane or UP and control plane or CP functionalities. The DU components that takes care of physical high layer, MAC layer, and RLC. And then we have the lower layers, so the physical low and RF layers that are taken care by another component that is called RU. So RU is the radio unit, DU is distributed unit, and CU is the central unit. And with this disaggregation, we have that the functionalities are split among different elements, and we can map these elements in different ways. So in a sense that we can have, for example, multiple DUs that are controlled by a single CU, and then they control in turn RU. So for example, you don't need to replicate every time RU, DU, and CU architecture, but you can have a hierarchical approach where you have a single component that can control multiple components. We also have an further addition, that is the addition of what we call RIC, for RAN intelligent controllers, that are the ones in the middle box here. And the RICs, which are standardized by ORAN, which is one of the approaches for the open RAN of the next generation cellular networks, which is one approach in which we want to open the interfaces of the RAN to allow interoperability of components from different vendors. We have that ORAN standardized these controllers that can act at different time scales. So for example, we have a controller that acts at lower layers, lower levels of time loop. So this is called a near real-time RIC. And then we have another controller that can act at higher time scales for example, for controlling parameters and functionalities that don't really need a fast control, but can allow for larger time granularities. And this is called no real-time RIC, and you can see that in orange in the diagram. So I was mentioning Open RAN, and Open RAN, I was saying that allows for interoperability of components from different vendors. So for example, you can buy a component from one vendor and a component from another vendor. And since they all implement the standardized open interfaces, on paper, they can talk with one another and they can communicate with one another. And this thing wasn't possible in the older approach where all the components were taken care by from a single component that was the monolithic base station on the left here. We also have that all of these functions that are split between the run, they can now be instantiated on demand, so only when I need them, on an hardware that is not heavily specialized as it was in the prior generation of cellular networks, but the hardware is getting more and more generic. So imagine, for example, pretty much generic servers or compute nodes. And then you can instantiate the functionalities in software instead of having specialized hardware. Of course, you still need some specialized hardware, especially for the radio unit. It is the component that takes care, for example, of the transmission of the signal and reception. But then other components like the CU and DU, you can pretty much instantiate in software on hardware that is not built on purpose for the cellular ecosystem and is not, and that is general, basically. And another thing with this, we have the functionalities that are implemented in software, and they can also be controlled through software. And in this way, because of this, we can also implement some intelligence application that can control the functionalities based on what is actually going on in the network at that time. So for example, I can have some applications that are called X apps or R apps, for example, in Aura. I can check on the current status of the run, and then based on this, they can decide to act to enforce some control, acting on some parameter, like, I don't know, I want to change the scheduling or the slicing configuration, and so on and so forth. And they look at the current configuration of the run, and then they enforce some control actions, sending it back to the run, because they're instantiated on the controllers over here. And then the run, so for example, the CUNDU will implement the policy that was sent to them and hopefully reach some goal that can be the optimization, for example, of some network performance. And this is just, in a couple of words, one of the recent evolutions of the cellular network, which is the scenario that we're considering. So with this evolution, we have that since we can instantiate multiple functionalities via software, we have that many softwares have started to arise in the cellular ecosystem. So for example, we have software like OpenAir Interface or SRS Run that allow users to instantiate base stations, both LTE and 5G base stations on this generic infrastructure and do, for example, experimentation or prototyping. And that this is a thing that until a few years ago wasn't possible at all. Now with this software, you can instantiate with your computer a cellular network in a matter of seconds, and then you can start experimenting with a standard compliant approach. We have some software that takes care of the control. For example, what you see here as SD-RAN or software provided by the RAN Alliance can be used for the control of the network. So for example, they can implement the rigs that are interfaced with the CU and DU, and they can host the intelligent applications that I was mentioning. And then we have other applications for core network, for example, or for the edge cloud or the EPC or 5G core. And this is just to show you some of the software that is available right now and that needs to coordinate with one another to have a functional cellular network working on the ecosystem. So this ecosystem, as you see, is very much complex and is getting more and more complex because now we don't have a single unit that takes care of everything. This unit used to be a black box, so meaning that you cannot really look into the code, you cannot really change the code, you don't have much flexibility. To this open vision where you can control in software and change and adapt if needed. So with all these software that we have and all of these components, we can do certainly a different number of things. So for example, we can implement some intelligent control loop to achieve some objective set by the operator. But which is great, but also with all this software, we need to test that the components still work in concert with one another, because at the end of the day, we want a working cellular network. So we come at this point, we come to testing the OpenRun software, and we figure out that it's pretty much complex to do, because we have, for example, different components that we need to test. And we don't only want to test them in a single manner. So we don't want to just get the base station and test that the base station works as it's supposed to be in a confined environment. But we want to test our base station, for example, in the ecosystem, in a complete ecosystem. So in an end-to-end ecosystem that, for example, is the one that I was showing in my previous slide. And to do this, the steps that you will need to take are, for example, you take one of the softwares like Open Interface or SRS Run, and you deploy a base station on a server, and you connect the base station to some radios. And then you can use the base station software to serve some users. So you can deploy some users that can be other radios, or they can be cellular phones, like the one you can buy at pretty much any store. And then after you deploy these cellular phones, you want to exchange some traffic. So a test that you can do is to use some software like iPerf, or other software to generate some traffic and benchmark or measure the performance of your network, because you want to make sure that your network can work as expected. And then you may want to test the intelligence. So you deploy a rig, so a run intelligent controller on some other servers, and you connect it to your base station. And then you deploy some applications like XApps on the near real-time rig, and you interface the XApps, deploy them on the rig, and interface the XApp with the base station, get real-time data from the run. So for example, keep performance measurements. And then based on this, you enforce some control on the run. And this is really an oversimplification of the whole testing process. So even though we're simplifying things a bit, you can already see that this is becoming more and more complex, and that testing all of these manually, especially, is very time-consuming and very complex to achieve, because I need to deploy every single component. Like I need to deploy the base station, the users, I need to connect them to exchange some meaningful traffic to test my software. I need to deploy the controllers, the XApps, and so on and so forth. So since doing this manually is very time consuming, and probably by the time I'm done with my test, I have that new versions of the various software that I'm using is already out. So I need to start all over again with my testing. The question is like, is there any way in which we can automate all of this? So is there any way in which we can avoid to do manual things, or reduce the manual operations to a minimum, and rely on some automation workflow to deploy these? So the short answer is yes, and we will see in the remaining of this presentation how on a possible way to do it. But let's maybe stop here for a bit and talk about some possible technologies that can help us in doing this. So as possible technologies, we can consider some technologies for CI/CD. So CI/CD is continuous integration and continuous deployment. And the whole concept is that you want to continuously integrate the new software on your architecture, and to deploy the new software as it comes out, to have always up-to-date software. And this is not really a new concept for cellular networks, but existed for other kind of software engineering approaches for multiple years. But the unique challenge that we have here is that we are operating, and we are not only operating just an edge computing kind of workload where we have a server and we instantiate some applications that are just compute load on the servers, but we have a novel component, which is the run part. So here we need to consider also a new kind of challenges that are challenges that regard the users part. So we need to serve the users at the end of the day, and we need to serve the users with some radios. So we have radio resource involved in this control loop, or in this CI/CD, which really make unique challenges. So going back to the CI/CD technologies, so some possible technologies that can help us in doing this deployment, automation, and testing are, for example, some containerization technologies, where we have network loads that are not instantiated on the bare metal server, but they're instantiated in kind of a virtual environment. So, for example, Docker, if you're familiar with Docker, or other approaches similar to Docker, that let you simply package an application in the form of an image, and then instantiate on demand, so only when you need it, the application on your compute infrastructure. And possibly you can also transfer the application out to different pieces of equipment, so to different nodes in your compute infrastructure. And other technologies are technologies for managing the infrastructure and the containers that we build. Some of them are Kubernetes and OpenShift. There are other technologies for sure, but these two are two technologies that take care of doing the lifecycle management of the run, for example, as we use it, or of a compute infrastructure in a more broad manner. And they manage the lifecycle of your container, meaning that they will take care of deploying the container, of destroying the container when you don't need it anymore, and to interface the container with the physical machine, so with the server, and potentially, if you have radios, as in our case, with the radios as well. We have some other approaches which are for DevOps and GitOps. So, for example, you might have some approaches that take care of synchronizing the configuration on your whole infrastructure. And such approaches are very handy, so you can keep your configuration for your infrastructure in a single version control source, like GitHub or GitLab. And then you can, when you update your remote source, you can push changes on your infrastructure, and your infrastructure can update accordingly. But in this way, you start from a quote-unquote written in stone configuration, and then you also reduce the possibility of any human error, since you also automate not only the software but the configuration on the servers. And then finally, we have some approaches that use automation, and they basically let you define some pipelines or some workflows. So let's say a series of steps that you can take out on your infrastructure to achieve some objective. And in our case, the objective is, for example, to continuously deploy new software and to test new software components and to verify that they don't have degradations. And we're focusing on software for Open Run specifically. And these are some of the softwares that we use to do so. They're certainly not the only ones available, but they're some of the most well-known softwares. That said, to talk about some common approaches for CI/CD, as I was mentioning, that CI/CD is not surely a novel concept. Many approaches exist, right? So we have some software or some approaches that actually focus on some compute-only workloads. So, for example, not interfacing with radios or with the run, but some workload that you can execute on some machine, and then the workload or the application will perform some tasks that are pretty much confined to that single machine, or they are communicated with other machines. Some of these approaches verify the successful build of the software. So I can write some piece of software, and then when I commit the software on GitHub or GitLab, I can have some automation that tries to build the software. And then if the software build passes, I can further test some functionalities of the software. And if that also passes, I can release my new image or my new software on GitHub making sure that the software can build and the software can execute the basic functionality tests. And we have some approaches that do so, and we have some pros and cons. So the pros would be, I have some software and I can automatically verify that my software builds and my software can execute. However, as I was said, we are focusing on the run part, and this kind of workload doesn't have any interaction with the run. So from our perspective, is pretty much straightforward because everything is confined to machine operations on some servers without the need to interface with external components that can be radios and users, for example. Other approaches are to transition, so to move some workloads typical of the run into microservices. So imagine you have a single piece of software like that of the core network that can take care of different operations from user management to serving data to the users to interfacing with the base station. And now you don't want to have a single piece of software that does this, but you want to split your giant software into micro components or microservices that each one take care of a single task. So for example, a task can be user management. Another one, I want to serve the data to my user, or I want it to interface with the base station. So we have a pro, and the pro is we have an enhanced automation and control, and we can also upscale some of the components if we need to without replicating the whole software. But again, in these approaches, we don't really have an automated run instantiation. So the run part is not deployed or instantiated automatically, or we don't have that testing is performed over the air. So even if they may instantiate some of the components automatically, we don't have the testing part. So the components are not tested over the air in a part of an end-to-end ecosystem. We also have existing CIs, like the one from Open Air Interface, which is one of the base station and user software that I was mentioning. However, we have that this software is tested in a confined environment, and for mainly quality assurance. So they want to make sure that the software they release actually works. So they have run core network. They do some testing with users or radios. And however, the testing is done in confined environments, and only a limited subset of tests can be carried out because that's the priority of the project. For example, the priority is to test commercial UEs and not software-based UE, which are here called softwareized UEs. And also all of this is not deployed on a production large-scale infrastructure. So these are some of the common approaches with some pros and cons and problems that they might have. So based on this, we have a sort of wish list of things that we would like to have in a sort of workload like the one that I'm focusing on. And a component is surely I want to have a CI/CD, so continuous integration and deployment of software for the run as part of an open run environment, which is the scenario we are considering. I want also to integrate this CI/CD and run environment in a real-world platform. So I don't want to just use computer software or simulations, but I want to have some real-world platform component. And this can include radio devices, user devices, or large-scale platforms. I want to be able to automatically and continuous test my functionalities of the run. And I want to test in an over-the-air environment. So with radios and users deployed in an actual real-world setup, but also in an emulated environment, as we will see in the rest of this presentation. And then I want to evaluate how the new software affects my KPMs, so my key performance measurements, to understand if it's working well or not, and if I have degradations. And then overall, I want to simplify the development and testing of the software. So I'm doing all of this to have a streamlined workflow for deployment and testing, because I also want to simplify the development of the software for the Open Run ecosystem. And that said, let's move to the first part of the testing use cases, which is the over-the-air testing in an actual real ecosystem. So let's say we have OpenAir interface, which is one of the softwares that I was mentioning, that they make base stations and users software, complying with the 2GPP specification. And we introduce, together with our CI/CD, a new component, which is the CT, which is the testing. So let's say we have a functionality that we wish to test, and we can wrap this functionality as part of a patch that can be applied to the new software that is already out. So I take the new software and I want to program some new functionality that I want to test. And these two operations I pretty much need to do manually, so development of the new code and then make a package out of this code. But then the objective is that all the rest of my pipeline that I will show you happens automatically without the need for any human interaction. So in a quote unquote run and forget manner. So I can run and then check the results when they're done. So the first step is that I want to take my patch and apply that to the most recent code. So I have some component that takes the latest code from the GitLab repository of this OpenAir interface project, applies the patch to the source code, and then builds the source code plus my patch in a form of Dockerized container. So this Dockerized container, container can be Dockerized with Docker or with other technologies like LXC, depending on which test bed that you want to use. But the important thing is that you build the software in a form of a container, and then you can use this software to test. So we have an over-the-air environment where we have some base stations deployed through this software. So I take my container that I built, I deploy that on generic software on top of Red Hat OpenShift, which is the orchestrator that I was mentioning earlier. And so in this way, I have my base station that is up and running. And then I have that the base station can trigger some users, like the one you see in the picture here, which is a 5G modem, and execute some tests over the air, like the hyperv testing that I was mentioning earlier. Or I can have another form of testing, which is the one on Colosseum, which is an emulator that I will cover later on. So you can imagine this as a large data center with servers and radios. And we can use some other tool like Ansible to deploy a container on top of Colosseum. So similar concept. I have a generic purpose infrastructure and I have my container and I can start my base station. And in this case, I can also start my users in the form of a containers with software-defined radios. I can run my tests. And then after my tests run, I can analyze my results. So I can collect my results. Build in also day by day, I can build a history of results and compare the most recent test, that is testing my patch and the latest version of the code, with the history of results to understand if a test that I run actually passed, which is good, or failed, which is bad. And in this case, I can produce some logs for the developers to look into. All of this is pretty much abstracted and it's pretty much simplified, but at a high level, what the diagram can look like of the infrastructure when we run this, it looks pretty much like this one. So we have some servers that are controlled through OpenShift, and some of them act as control plane nodes. And on the control plane nodes, we can deploy different services that maintain our infrastructure, so interface with OpenShift, and also run different applications that don't really need specialized workflows, right? So we can run our rig, so our controller, our core network, and our XApps. And basically all these services that are non-really time sensitive. And then we have another set of nodes that are called worker nodes that need some specialized applications, which are some specialized configurations, which are, for example, I might need a very low latency kind of kernel to take care of operations in a faster way, or I need some connection with the radios, right? So I want these servers to be able to communicate with my radio devices, because these servers will eventually be the base station servers that I'm testing. So this is at a high level the architecture. Then there are some other components like networking architecture, image registry, and so on and so forth. But at a high level, we have some control nodes that take care of non-time sensitive operations, and then some faster nodes that take care of latency sensitive operations like the base station. And just to have a quick dive, in a more deeper manner, we have the previous pipeline, which was pretty much abstracted, that can be let's say, depicted like the diagram here, right? So we have many components and many operations that are taken care of into each one of them. But at a high level, we have some operations, so marked here with number 1, that takes care of periodically triggering my test, right? So I have some tasks that at a given time of the day, they will start the rest of my pipeline, which is the pipeline that we use to build, deploy, and test. There are other steps, so steps from 2 to 5 here, that will compare the latest release of the software from Git, for example, with the one that I already have deployed on my infrastructure. And they will tell me if I'm already using the latest version of the software or if I am behind with the software version. I have some other steps that, in case I'm behind, they will build the new software version, and if I need to apply some patch, they will patch the software version. And then I have some instantiation components. So I will take my Docker image and instantiate them on the infrastructure on my previous slide in a form of a container. So this is, in my example, to instantiate my base station. And then I have some components that automatically test once my base station is deployed. So they will perform the hyperv test that I was showing. And then other components that will save the results. So it turns out that out of all these operations, there are some operations that are kind of straightforward, and then some operations that are instead kind of complex. And if you notice, the complex operation is the one that regards the testing, because it needs to interact with components that are outside of my system, and if you will, in a manner outside of my control, so the users, for example. And all of this was implemented on OpenShift in a form of some pipeline. So for example, here you can see the pipeline to build and deploy the new image. So the steps, the first steps, the middle steps that you had in the previous slide are taken care by a pipeline like this one. So you have various steps. So 1 step to build, 1 step to clean up, and 1 step to deploy. And the pipeline is based on a software that is called Tecton, that, without going into many details, lets you define a series of steps to complete as part of my pipeline. And each step can have several sub-steps. So here are only shown some of them. I have some other software that is called Argo CD, which takes care of configuring my workloads and my servers. So for example, I want my server to have some configurations and my workloads to have other configuration, like for example, to be able to connect to the radios. And the configurations are kept on a version control system like Git, and they can be deployed with software like Argo CD. So I minimize the human interaction to also minimize the human error. And then I have that I can trigger some pipeline to test with the Open Interface G0B and the modems that you were seeing in my previous slide, which are called Sierra Wireless modems, and they're commercial 5G modems. And then I have that overall my pipeline is a series of steps with multiple sub-steps that we run. So a pipeline like this one, where the testing here is not shown for simplicity, was actually deployed and testing continuously on an over-the-air infrastructure, which I call Arena, that we call Arena in the lab, which is a test bed with servers and radios deployed on the ceiling of a lab space. And this pipeline automatically ran for more than 1 year at this point, even if here only 9 months are shown, multiple times a day to try different configurations of testing, like you can see 10, 20 megabit per second hyperv configurations, and different configurations of the server. Like for example, you can see we have different configurations with first a real-time kernel, and then a generic kernel on the right. And as you can see, we have through this system, we can see that there was some issues with the first configuration that we had, so the one on the left, the purple line. And then once we changed this configuration, we got test results that were kind of more stable, and we could rely more on them to actually spot errors with the software, degradation with the software, and not actual issues with our infrastructure. And we can see this at a glance. Another thing that we can do, we can build a history of results, shown here with the solid lines and the colored areas. And then we can see if a new test is within boundaries of results. So for example, the test with the dashed line is the new one. And here we have on the left an unsuccessful test because the dashed lines are not in the confidence intervals, so not in the shaded area of my history of results. While on the right, you see what a successful test might look like, because I'm within a reasonable confidence interval of my history of tests. And through all of this, you can see at a glance if the test succeeded or not. And after doing this over there, we said, okay, now we need to do it at scale on an emulated environment, which is the environment provided by Colosseum. So just to give you a very quick overview, Colosseum is a giant data center with 256 software-defined radios. So the ones I'm using over there, where I have maybe 10 or more. Here I have 256. So I can really scale up my environment. And the concept is similar. I can deploy containers on top of my infrastructure. And then I can use my containers to test. The main difference with my previous approach is that now I also have users that are implemented through these software-defined radios, so I don't have commercial devices, but I need to rely on radios for both my base station and my user. And then on Colosseum, I also have some GPU resources, which allow me to take care of more complex tasks, like computing-intensive tasks that can be the ones taken care of by the intelligent applications that I was mentioning. So I can train some applications on these GPUs and then use the GPU power to run applications that might be heavy to execute on GPUs. And at a high level, the diagram of Colosseum looks something like this, where we have different components. And the different components of the Colosseum infrastructure can be somehow mapped in the Oron ecosystem in some meaningful way. So we have, for example, a component that is the massive channel emulator that reproduces reproduces wireless environments. So I can characterize environments a priori, like the one shown here. And then I can capture the channel impulse response and reproduce it with Colosseum in a way that my experiment run in that specific emulated environment looks very similar to what I would have running in the same setup on the real environment that I characterize a priori. And then I can have my servers, which are also called SRNs, that implement the base stations on the right of the top diagram and the users on the left of the top diagram. So I basically instantiate different cells, like 7 cells here. And I instantiate 6 users per cell. So I have a very large scale compared to what I can have in a lab setup with only a few radios. And I can communicate between base station and user over the emulated scenario that implements a real-world deployment, for example. I have the intelligent controllers that can be run on GPUs, and they can interface with the base station to implement my intelligence. And this is just how some of these components can map on Colosseum. I mentioned that I'm actually emulating the channel, but what does this mean? So the fact that I'm able to emulate the channel means 2 things. So the first thing is that I don't have a real over-the-air channel. And this might be good or bad based on what I want to do. So I don't have necessarily the same accuracy I would have on a real channel. But the pro is that since I can emulate the channel, I can reproduce different kinds of channels, basically reproducing my experiment in different setups and configurations. So the way it works is that my user radios, which are the ones on the left here, communicate directly through cables two other twin radios that are controlled by what we call massive channel emulator. So the signals that arrive to the emulator are processed by the FPGAs here, applying the channel taps that I characterize a priori with my scenario. So I characterize my scenario, I generate some channel taps, and I apply them in real time to the signals that arrive from my radios. In this way, I do some convolutional operations in a way that the resulting signals are similar to what I would have for the environment that I'm reproducing. And then the signals are sent back so that my receivers can receive them in a meaningful way. So if I'm emulating an outdoor environment, the signal here will look like the same as I would have running the same experiment in a outdoor environment, and similar for other kinds of environments. So in this way, I can emulate different kinds of scenarios and different kinds of environments in my ecosystem. And this is pretty much the testbed environment that we are using. So the pipeline on Colosseum is based on some other software. So it's not based on OpenShift, it's based on Ansible. Ansible gives you, at a high level, a series of tasks that you can put together and run. So for example, here I'm running what is called a playbook. So this series of tasks. And the playbook defines a series of steps that I want to carry out with my tasks. So a step could be, for example, I want to build a new container image of Open Interface. I want to deploy some patch. And then I want to automatically instantiate my container on Colosseum. And here on the right, you see an animation of the Colosseum automated testing portal that I've been developing. And you can see that you can select from a series of tasks the task that you want to run, and then you can easily launch a task just by clicking a few buttons. And the task under the hood looks something like this. So a series of roles, to talk in Ansible jargon. And each role has different steps, so different sub-steps. So a role can be, I want to create a basic container for the Colosseum infrastructure. And then another role can be, I want to install the dependencies that are required by my software. So for Open Interface, in this case, since this is the playbook, so the task for the Open Interface workload. And then after a while, once this ends, I want to save or export my container image in a way that I can then deploy that on my infrastructure and run some tests. And this is what the previous playbook that I was running just by a click of a button on the dashboard can look like at a very high level. And I won't dwell in the details of each of these roles, as it will be kind of tedious and kind of long. But at a high level, imagine this as a series of steps with a series of subtasks. The nice thing of doing this is also that we can benchmark each task. So for example, I can have a recap on the various tasks that I run, and I can benchmark how long it took to do the tasks. So you see that the task that it took longer here was to execute the test that we call a batch job on Colosseum. So an automated job is called a batch job. And this is because I set my duration of the test to be 24 minutes. But then, excluding this, the longest part was to actually build the image with all the dependencies and so on and so forth. And this is nice to have a benchmarking to understand how long each task is taking. Of course, this is not just limited to Open Interface, but all of this can be extended for additional use cases and other protocol stacks, even though I'm providing Open Interface as an example. And for example, I can also use it for automated data collection with other software, like with the SRS run software, that is the other software that I was mentioning, that takes care of similar functionalities as to Open Interface. And this was used to collect at a large scale some data set that we recently made available. And then I can also use these to test new functionalities. So some DApps, which are real-time applications that we at Northeastern are proposing for Orange standardization, so I can test the functionalities in an automated way at a large scale on Colosseum. So this becomes also pretty much handy, not only for testing base software components, but also to test modifications in addition to such components. We integrated this with Eurecon, which is the entity, the research consortium that is actually developing the open interface software, so that they can also use our software to test automatically on Colosseum. They use Jenkins, which is another software. We use Ansible, but the two take care of similar tasks. So we have some, we have them put together some pipeline that they can use to test with different emulated environments or different scenarios, so outdoor, indoor, large or small scale, or others you can imagine, with different mobilities and so on. And then they can collect results and save them in what Jenkins calls artifacts. So I can save, for example, some logs or some summary of my test. And the summary of my test is really a report that I can build automatically once my test is done. So once my test is done, some results will be collected. And then I have some software that can go through such results and package them in a nice way that is easy to understand for a developer to look at a glance and know if something is going on. And the report looks like something, looks like what I have here on the right of the slide. And of course, I can compare with the history of results. So if you see, I have a solid line, which is the time evolution of my throughput in my test, which was an hyperf test. And then I have a blue dash line, which is the average of this run. And then I have a dash red line, which is the history of collected results over time. So I can say, oh, is my test above or below the average? Or if it's below, how much below it is, and so on and so forth. And by doing this, I can also set a criterion for passing a test. So for example, my criterion here is the throughput at least 90% of my history throughput. And based on this, I can determine if a condition that I set for my test, so for example, is throughput at least 90% of the history, if my test passed or not. And I can include additional information for debugging. So for example, which node of Colosseum or SRN I was using, which commit I was using. And then together with this, I can pair some logs that the developers can look into. And so I was mentioning, we integrated this with the open interface code. And this was merged just a few weeks ago. And this took pretty much 5 months to converge to a solution that could be merged in the open interface code, so that now the developers of open interface can trigger automatic tests on Colosseum to have some further insights with respect to the tests that they regularly run. And since we made the report generation tool, we also decided to make this tool open source so that people running experiments, for example, on Colosseum or in other environments, they can just give the results to this tool and end up with a report very similar to what we had in the previous slide. And this is also to help the open source community. So this is the pipeline in Jenkins. So I can, for example, select some parameters. Let's maybe go back from the beginning. So I can just select some parameters and insert some parameters, like one parameter can be the build that I want to insert. So here the develop branch open interface, and then I can click build, and then my pipeline starts. Once my pipeline starts, I have a series of steps, and the first steps will be interface with Colosseum, because this is running on another infrastructure in France. And so I would wait for connection to be established with the Colosseum testbed, and this can take a few seconds. And then once the connection is established, I can actually see that on Colosseum, I have a new test that is starting. So the new test is called a batch job, because that's how we call automated tests, which are tests that are configured a priori. And then they're started on Colosseum just by inserting a queue. So I can select some of the batch jobs here. And then I can actually put them in a queue, and Colosseum will run them once resources are available. So the batch job that I just started with my Jenkins pipeline in the video is here, and it's running in Colosseum, and the duration you see is 24 minutes. And then after fast forward 24 minutes, I see that my pipeline will wait for my job to finish. And then at the end, we'll grab my results to save them in the Jenkins server. I can see that my test succeeded in this case, and I can find my results as a test summary here, which is the report I was mentioning, and then also as part of an archived collection of logs meaningful to the open interface developers. So the test result looks really like something like this, where I can see different tests. I can plot my different tests, and I can see ultimately if my test passed or my test failed based on some condition that I set in the beginning. And all of this is nice because we can, first of all, see at a glance if something is going on, but also with this report generation tool, the report and the pipeline, we can help the open source community and to test and to reliably develop software for Open Run, and in a way also to give back to the community for developing this software and approaches that we use for experimentation on real-world equipment and testbed. So overall, to sort of draw some conclusions, so we saw that one of the possible approaches to do continuous integration, deployment, and testing for both over-the-air and emulated environments. So over the air, we had what we call Arena, which is a testbed for experimentation with radios and antennas deployed on the ceiling. In this case, in Arena, we use commercial 5G modems or commercial phones as users. And we use software-defined radios as base stations, but we're expanding this to commercial radios as well. And we also saw this in an emulated environment, where the main difference is that we're not using commercial phones or modems, but for the users, but we're using software-defined radios. And this is on one side good because it allows us to expand our set of tests that we can do. And also by doing emulated environments, we still have the same radio that we use over the air, so the radios are real, but then we can test with different scenarios. So one of the tests that we carried out is to test with the same scenario on the over-the-air testbed. We characterize that and test on Colosseum. So that we can go much farther than this and test in very diverse scenarios with user mobility and different characteristics like outdoor, indoor, large or small scale, and so on and so forth. We saw that this is complex because we have to account for different things, but it's pretty much feasible. And then after programming this, we ran this pipeline for several months. I showed here 9 months, but the pipeline has been running for multiple times a day since July 2023. So it's more than 1 year at this point, where we have from 4 tests per day to 7 tests per day. And we also have that the release of the software open interface is also updated as new releases come out, and they usually come out on a weekly basis. So we have that we're testing with the latest version of the software, or at most 1 or 2 releases behind by the time that the software updates. And we saw that our system that we assembled to do this automation of testing and deployment has a very good potential and can be extended with different use cases. And finally, we integrated this with the IRECOM, which is the research institution that develops the open interface software, for testing their GNOT-B and software DOE software on Colosseum in different scenarios, different mobilities. And we also open sourced the tool that we use to generate the report to kind of help and give back to the open source community. And this was it from my side, and I hope you enjoyed my presentation, and I'd be more than happy to answer any questions that you might have. And thank you for the attention.